Hi and welcome. I'm trying to learn biochemistry today, inorganic acids, bases and salts. And after we've done it, we're going to do leg injury prevention training. And if you participate in the leg injury prevention training, that is better get on with this. And we're talking about internal anatomy. When inorganic acids, bases or salts dissolve in water, they dissociate. And that is, they separate into ions and become surrounded by water molecules. Okay, we're having the salt or the salt crystals over pure acids, over bases. And when we're dissolving, these ions, which compose more or less the chemical element salt, acid or base, is separated and then surrounded by water molecules. So when we have when one ion and when so much water molecules around them. And that is when dissolved. And now we're having water with a lot of parts of salt in it. That is how it works. We have salt crystals, and they are now in the water, and if they are dissolved, the water comes in between them, and around them, one single ion of salt is there now with some amount of salt water around them. An acid is a substance that dissociates into one or more hydrogen ions and one or more anions. I don't really know what an anion is. Okay, acid seems to, that is interesting. Acid seems to have a definition what an acid is. And acid seems to be every type of substance or a substance which, if it is dissolving now, or dissociates thing, it becomes one or multiple hydrogen ions and then also anions somewhere, somehow. Because H plus vis-a-vis hydrogen ions is a single proton with one positive charge, hydrogen plus. With one positive charge, an acid also is a proton donor. Now it will be important, we had already made lipids, it is important if they are electronegative or positive or proton donor, whatever, how they can now form bonds with other types of substances in the human body and become through that a substance or being dissolvable in the blood or transportable. So it is important. And we are not now told that acids are dissolving into or dissociating into one hydrogen ion, which is plus, so it is a proton donor. It has one so much of positive. It has a proton. Everything with a proton is plus. Everything which has more proton than electrons. And this thing here has a single proton and now electrons, so it is a plus thing. It is a proton donor. It can give away a proton. And also anions. A base, by contrast, now we're having something else. A base, by contrast, dissociates into one or more hydroxide ions. Hydroxide ions and one or more cations. I don't know which one as well as the anions. So we somehow have to find out what anions and cations are. But the base, they are negative. Or whatever. If they are dissociating, they become negative. They are becoming hydroxide ions and they are negative. So acids and bases are fundamentally working different in the human body. Acids have one proton too much, they can bond with something else, and bases, whatever even bases are, can hydroxide ions negative that if they have dissolved in water. Because hydroxide ions have a strong attraction for protons, a base is a proton acceptor. Yes, they are negative. We know that bases, if they have dissociated, become negative once hydroxide ions, they are negative. They are lacking and proton, they are negative, they are in the minus. And the hydrogen ions, they are plus, they have a proton too much, and now they're perfectly fitting together. The proton donor hydrogen ion has one proton too much, and the hydroxide ion has one electron too much, or whatever, a proton too little, and now they're perfectly fitting together, and they both now building one pair. A salt, when dissolved, it is a proton acceptor, so we have to have it word also. Proton donors exist, they have a proton too much, they want to give away a proton, and proton acceptors, they seem to be negative, they want to get one. They want to accept one. A salt, when dissolved in water, dissociates into cations and anions, neither of which is H plus or H or 0 or OH minus. Okay. A salt, okay, we had 3 examples told you. Then human body acids, they are proton donors. They have a plus too much and they want to team up with things which have a minus. For example, bases, I don't know what it is. They are minus. They are teaming up these two stuffs in the human body. Salts, not. They are becoming cations and anions. And they are neither H plus or OH minus. H plus, that is hydrogen ion, and OH, that is hydroxide ions. The H is for hydrogen, and the O is for oxide, hydroxide ions. In the body, salts are electrolytes that are important for... Now it explains the thing with the electrolyte, all the things. No, the first thing which I noticed, cations and anions. We were told that the hydrogen has an anion, and the hydroxide has a cation, or more cations. Whatever they now are, whatever we have to do, they seem to have something to do with whether it is plus or minus. We have a hydrogen, which is plus, more protons, has anions, and we have a hydroxide, negative, and it has cations, and now we have a salt, which has anions and cations. And it is more or less neutral, seems to be. And that makes it possible for, in the body, salts are electrolytes that are important for carrying electrical currents. Ions flowing from one place to another, especially in nerve and muscle tissue. Because they're neither plus nor minus, these salts are perfectly there to transport electricity through the human body, and this signaling of electricity, like a lamp signals over nerves or muscles, what we have to do or what is happening. And that explains a lot. Okay, the salts are just chemically in the human body consisting out of cations and anions. They are neither plus nor minus, and therefore they are able to make the electrolysis, which is sending electrical currents through the human body over nerve impulses or muscle impulses to tell the muscle where to work or what the nerve is feeling, whatever. The ions of salts also provide many essential chemical elements in intracellular and extracellular fluids, such as blood, lymph, and the interstitial fluid of tissues. Okay, they're also important for the cells itself. Whatever they are doing there, they're also important for the cells. They're intracellular and extracellular fluids. It's not part of cells. Such as blood, lymph, and interstitial fluid of tissue. Okay, they're also important in the blood and in lymphs and in other things. Acids and bases react with one another to form salts. Let's see it over. For example, the reaction of hydrochloric acid. Hydrochloric acid, HCl, hydrochloric acid, HCl, and potassium hydroxide, KOH. A base produces the salt potassium chloride, KCl, and water, H2O. This exchange reaction can be written as follows. Now, I don't know if I know the on for it. This dissociation is the separation of inorganic acids, bases, and salts into ions in a solution. HCl becomes hydrogen plus and chloride minus, and let's try to go back. So acids and bases react with one another to form salts. We have the acids which have anions, they have one proton too much, and they are positive. And we have the bases, they are hydroxide ions, whatever, and they are minus. They have cations. They both team up together and form salts. Salts can be used as in the electrolysis, whatever, as electrolyte, and that helps to send feelings and orders through the human body. So now we're having a reaction of hydrochloride acid and potassium hydroxide. And one of them is an acid, the other one a base. Hydrochloric acid is the acid, and potassium hydroxide is the base. And they are producing the salt potassium chloride. I know that common salt, which is eaten, is sodium chloride. Now we're having a potassium chloride. That makes all sense. Okay, the salt now here formed out of hydrochloric acid, and potassium hydroxide is potassium chloride. And also water is formed. Or water is used by this reaction to make this. And this exchange reaction can be written as follows: HCl plus KOH, which is now hydrochloric acids together with potassium chloride. Potassium hydroxide are becoming hydrogen plus chloride acid minus plus potassium plus oxygen hydrogen minus, and these are these dissociated ions, and they end up to be then potassium hydroxide acid and just potassium chloride and one moment, the hydrochloric acid, the I, is an L at the end of the day. It is hydrochloric acid, it's hydrochloric. Otherwise the KCl wouldn't make sense. It's just potassium chloride, and it has KC, not I but KCl. It's potassium chloride. I don't know. And we end up now with salt, KCl, potassium chloride, and H2O, hydrogen, 2 hydrogen, 1 oxygen, water. Now, this was certainly not something which should explain us something in detail right now, which was the groundwork for many things which will be explained in the future chapters. We just let that sink in and come back later and give the information we understood and can repeat them together and make them a presentation about that part. But for now, that was the biochemistry part. If you were here for biochemistry, you can go directly to the next part of biochemistry. If you stay here and participate in the too short 3-minute leg engine prevention training, then is it at your risk. Having a good standing, no, we have not. We have both legs standing around hip wide apart. We're going a bit down, and now flex the upper legs and also press with the legs together and straighten one leg completely. Straighten it completely. Keep pressing together. Flex all the muscles in the upper legs and bend it again. And now bend the other one. Straighten over. And completely straight it. Press with the legs together, flex the legs, and back into the middle again, and release. And now something similar. Legs a bit apart, a bit down, and flex the legs and press them together. And now go over to one side again. Straighten the leg, keep pressing together, keep flexing the muscles, back into the middle. Press them together, straighten both legs, over to the other side, straighten the other leg. Press together, flex the muscles, and back into the middle. And up again. And now have a good standing leg, the other leg in the air with a flexed foot, and swing it in front and to the side. And over to the other side. Have a good standing leg, the other leg in front and back. And stand good and over the other foot. And now breathe in the front leg up and go over to one side. Change. And over. Change. Other leg up, hands up and go over to one side. And to the other side. In the middle and again down. And now stand good on one leg, turn over to the leg, this can go into the knee, go down into the knee, over to the other side, and come up again. Slowly and concentrated, stand good, turn over, go down, over to the other side, and come up again. And with the other leg, stand good, turn over, go down, to the other side, and come up. And again, stand good, turn over, go down, over to the other side, and come up. And we're ending already. Legs wide apart, breathing good on. And breathing out. Again. out. Breathe in, close the legs. And breathe in, out. That was the shortened leg injury prevention training. I thank you very much and until next time.